Welcome, everybody. If you were looking at our day one of AP BC prep session today that Tony and I did, the first day of our 2020 focused AP exam prep was covering Unit 10. That's the unit with the 5 testable topics this year over convergence and Taylor polynomials. During our live YouTube session, which you can find on the College Board's Advanced Placement YouTube channel, Tony and I were able to work through the first 2 problems in the packet, BC1 and BC2. And we didn't quite get to BC3 during our live session, so I mentioned that I would make a short video working through this problem. Now, don't forget, the worked out, typed up solutions are also going to be available in the same Dropbox link as everything else. But I wanted to give you a voiceover recording because I want you to see some of the nuances of the problem beyond just the typed up solutions. I want to point out a couple of things that I think are important, things that you could think about, some exam tips, some possible pitfalls and misconceptions students might have that might lead to them not earning all the points on an AP question like this. So this will be a pretty brief video working through it, but I do want to go through it with you and kind of point out a couple of highlights. And so this one starts out with a Taylor polynomial. So the first 2 that we did in our videos, those 2 problems started off with convergence tests, but we're given a table here, and it's got lots of different values of f and f prime and f double prime and f triple prime at 2 different x values, x equals 1 and x equals 4. And then we're told in the stem that f and g are differentiable for all orders at all x values. And so we've seen this phrase come up a couple of times, differentiable for all orders. I want to pause for a minute because sometimes students get caught up on the words in the stem, and it prevents them from really understanding how to solve the problem when really it shouldn't. And so this differentiable for all orders just means that f has derivatives always, meaning it's never not differentiable. So you can take f prime, f double prime, f triple prime, the 4th, the 5th, the 6th, the 7th, that no matter how many derivatives you take, and no matter what value you plug in for x, you'll always get an answer. So it's never going to be a not differentiable type answer, right? And so that's important because when you're creating a Taylor polynomial, we have to have derivatives. And so we have to guarantee that these things actually exist. And so this is just telling us that. So a lot of times when you see those AP problems at the beginning, I always call this like the fine print. You know, when you buy you get a contract or you buy something, at the very bottom sometimes they'll have that really small fine print there kind of giving the details. This is sort of the details. And I always call it the teacher fine print, because if we don't include stuff like this, we end up getting emails or messages from teachers saying, well, technically you can't solve this problem because you don't know blah blah blah. And so we put those things in there just to say the things that you would expect to do, the things that you would want to do with this problem are actually possible, right? There's not going to be any contradictions or mistakes with it. And so that beginning part sometimes is there more for us to know we can do it, but it's not really going to play a large role, or really any role in this case, in actually working out the problem. It just tells us that we can do this problem. And so it tells us that the values for f and several of its derivatives, which we can see here, are given in the table above. And then it tells us that the function g, this other function g they mentioned, is given by this function g of x is 3 of x plus the integral from 4 to 4x of f of t dt. And so part A says find p sub 3, the 3rd degree Taylor polynomial for f, right? Centered at x equals 1. And so before you jump into these problems, organize your thoughts, right? It's a really good way to make sure that you're not skipping steps, first of all, and B, it's a good way of making sure that you're not falling into any traps or any of these little tricks that might end up, causing you a point because you're trying to do too much in your head too fast. And so when we know we're doing a 3rd degree polynomial, it means that n is going to be 3. And then the key here is knowing which function we're doing it for, because we have 2 different functions given, f and g. So we got to pay attention to which one. And the center is always important. That means that c is 1. And so I really like to create this blanket form that a 3rd degree Taylor polynomial for any function, we have sort of that formula for, right, that we developed last week. And so it's going to be f, in this case, that's the function we're making it for, of c, which is 1, plus f prime of 1 times x minus 1, and then f double prime of 1, x minus 1 squared over 2 factorial, plus f triple prime of 1, x minus 1 to the 3rd over 3 factorial. This is sort of our setup, right? And we knew to stop here because it was a 3rd degree polynomial. I used f values in my equation because it's a polynomial for the function f, and I used x minus 1 and 1 because that's where the center was, right? Those are kind of like the components of our Taylor polynomial. And then our job, if we're going to create this polynomial, is we have to plug in values for all of those f's, right? Whatever we get in front here, to create a Taylor polynomial, that's the part that you have to plug numbers in or find somehow. Sometimes they give you an equation. Sometimes they give you some values in a table. Sometimes they give you just some information, right? There's a lot of ways that you could come up with those values, and that's when we start going back to the information and say, okay, how do I find these values? Well, we notice we have this table of values, and I want to find all of those values specifically when x is 1. Hey, look at that. That whole first row of this table gives us each one of those values. And so our third degree Taylor polynomial is going to be f of 1, which is just -2, plus f prime of 1, which is 0, and then f double prime of 1, which is 3, times x minus 1 squared over 2 factorial. And then finally, f triple prime, which is 4, x minus 1 to the third power over 3 factorial. And so there is our third degree Taylor polynomial for f centered at x equals 1. Now notice I didn't clean this up. I didn't reduce it. You're always welcome to simplify and reduce. You don't have to include this second term here because there's a 0 in front being multiplied. You can not even include that. I like to just write it out completely and then realizing we don't have to reduce or simplify our answers. So I would just probably leave my answer like this on the AP exam. Now, obviously in my classroom, I want my kids to reduce and simplify this so I can see what their actual answer is. But because of the time constraints on the exam and because of the nature of how it's scored, that if you have an answer and you try to simplify it and you make a mistake, you're going to essentially not earn that last point because we have to read with you until you're done. And so until you're finished your answer, that becomes your final answer, right? And so you might end up not earning all the points if you try to go too far and make a mistake. So I would encourage you on this year's AP exam and on any FRQ to leave this like this. So then part B, same idea, right? Same stem, but now we're finding T sub 3, another Taylor polynomial. It's a third degree polynomial. The difference is it's centered at 1 still, but now it's for g of x. So we still see the same center. It's still a third degree. So everything is very similar to part A. The only difference is we're doing it for g. But that one tiny change, we're going to see this actually makes a really big difference in our answer and how we set this problem up. So this is where I like to really write out our general formula. A third degree Taylor polynomial for g centered at 1 is just going to be g of 1, whatever function you're making it for at the center, plus g prime of 1 times x minus 1, plus g double prime of 1, x minus 1 squared over 2 factorial, plus g triple prime of 1, x minus 1 to the third power over 3 factorial. So this is our, kind of building blocks for our third degree Taylor polynomial. And like always, since we're making a Taylor polynomial, our job is to compute all of those values. In this case, we're finding the g values instead of the x values. Well, it's not going to be quite as easy as part A, is it? Because part A, we had a nice table of all those answers there. We don't have a table for g. Our table is only for f, but we are given this little function right here for g. So I bet you if we organize our work, this is where being organized is going to be really helpful. We could quickly come up with all of those values. And so we know that g of x is just going to be 3x plus the integral from 4 to 4x of f of t dt. And what I like to do is find all those values. Instead of plugging 1 in right away, I like to just find them in terms of x first, do all of those, and then start plugging 1 in one by one. By being organized like that and showing those steps, it actually makes it go faster. Sometimes students think, well, I just want to plug 1 in right away without showing all the actual derivatives in terms of x. And you think you're saving time, but I think what happens is in the long run, you have to keep going back and thinking about what you really had before you plug numbers in. You end up spending more time doing it this way. and you're not as organized, so it's easier to get lost and a lot easier to make mistakes. And so I would recommend writing down all of just the functions that you need. We know we're going to need g, g prime, g double prime, and g triple prime. So I'm going to do those in terms of x first. And so g prime is just the derivative of this equation. So 3x's derivative just becomes 3, right? And then plus, now we're taking the derivative of this integral, right? This is a really good connection to Calc AB because we know how to take a derivative of a definite integral using that fundamental theorem of calculus, or maybe your book might call it the second fundamental theorem of calculus, depending on which order your book teaches those fundamental theorems. But we can take the derivative of this function by plugging in 4x, so it becomes f of 4x, right? And then we multiply by chain rule by the derivative of what we plugged in, which is 4. So really, g prime of x is going to be 3 plus 4 times f of 4x using the second fundamental theorem of calculus. If you forgot a little bit about that second fundamental theorem, when Tony and I do our connecting AB to BC ideas next week, we'll spend more time on that fundamental theorem again, refreshing it and also making more connections to how that might appear in other BC type questions. And then the second derivative, g double prime, we just keep taking derivatives. Well, 3's derivative now becomes 0. This other piece's derivative, well, f's derivative becomes f prime, right, of 4x. And then by chain rule, we have to multiply by the inside's derivative. So 4x's derivative is 4. We multiply by 4, but we already have a 4 in front. So that becomes a 16, doesn't it? And then g triple prime is another derivative. Well, now f prime becomes f double prime. The inside stays the same and multiply by the chain rule again. So multiply by 4 again, and 16 times 4 is going to be 64. So these are our values, g, g prime, g double prime, and g triple prime, but we have to find them where? At 1. And this is where keeping this so organized is going to be really helpful, because watch how easy it would be to make a mistake. So many times students will just immediately, because we're centered at 1, go back to that top row and just plug in those numbers, right, where x was 1. But notice, if we actually want to find all these values, g of 1 now, if I plug in 1 for x, we get 3, because 3 times 1 is 1, obviously. If I plug in 1 for this x right here, we're now taking the integral from 4 to 4 of f. Now, we don't even know what f really is. I don't know what the integral of f is, but it doesn't matter, because the integral from 4 to 4, since those are the same bounds, that integral is going to be 0. There's no area if you start at 4 and stop at 4. There's no width to that graph. And so the answer, Jared, just becomes 3. So g of 1 is 3. And then g prime of 1, which is the next thing that we need, is going to be, according to this, 3 plus 4 times what? When I plug in 1 for x, I have to plug in 1 for this x. Now it becomes f of 4, doesn't it? So it turns out I don't really need this top row when x is 1. I need to find f of 4, which is right here. And so g prime of 1 is going to be 3 plus 4 times negative 9/4. That's what f of 4 is. And if I reduce this, luckily the 4's kind of cancel, right? At first, when you saw that table, you're like, oh my God, he's giving me these horrible fractions. That's actually being nice. It's going to turn out pretty nice. And so the 4's cancel, and 3 minus 9 is just negative 6. And then g double prime of 1, the next term, is 16 times f prime of 4. Well, now we go back to the table. We need f prime of 4, which is just 3 halves. That's going to be 16 times 3 over 2, which reduces to the 16, and the 2 reduced to 8. What is that, 24, I believe, I hope. All right, you can correct me if my math is bad. And then I'm going to extend my screen here a little bit. And then the last one that we need here is going to be g triple prime of 1, which is now 64 times f double prime of 4. Well, looking at our table, f double prime of 4 is this negative 9/4 again. So that's going to be 64 times negative 9 over 4. Well, the 16 and the 4 do reduce to 16 and 1. And I don't really know what 16 times -9 is, but I'm going to leave it like that for right now because I don't have to reduce this, right? Obviously, you're going to have a calculator possibly on the exam with you, so you could reduce that on the calculator if you wanted to, but I'm going to leave it kind of like that for now because now that we have all of these values, we actually are now ready for our Taylor polynomial for g. So g of 1 we said was 3, and then g prime of 1 was -6, so it's going to become -6 times x minus 1. And then g double prime was 24, and that's going to become x minus 1 squared over 2 factorial, or just 2 in this case. And then g triple prime of 1 is 16 times -9, which is going to be a negative number. 16 times 9, whatever that is, times x minus 1 to the third power all over 3 factorial, which is 6. So this is my Taylor polynomial, and we could actually leave it like that. This is all part B wanted. I'd probably just leave my answer just like that. I wouldn't take any chances of reducing it, even if I had a calculator. If I need this answer in part C or part D, then when I get to that part, I might reduce it because it's easier to reduce them before you do the rest of the math typically. So I would leave my answer like this, but just for our purposes, I'm going to go ahead and reduce it on here. So that way we can have a nice reduced answer because I think we're going to use this again in part C. So if I have 6 on the bottom, the 6 and the 16 can both be divided by 2. And then also the 9 and the 3 can both be divided by 3. And so really what I get is just minus 24 x minus 1 to the third power. So once I reduce this, it kind of became a nice little simplified answer. It turned out to be pretty nice, didn't it? And so looking on part C, it says, okay, let this thing, we started off with Taylor polynomials, and now we're introducing geometric series. What? Let's see where it goes. So let A sub n be a geometric series whose first 4 terms are the 4 terms of T sub 3 found in part B. So to remind you from part B, this is what we came up with, right? We said it was 3 minus 6 times x minus 1 plus 12 times x minus 1 squared minus 24 times x minus 1 to the third power. That was what our reduced third degree Taylor polynomial was. And it's telling us we've got this geometric series A sub n, right, whose first 4 terms are just these. So what they're telling us is that A sub n, the series of A sub n, is just going to be 3 minus 6 times x minus 1 plus 12 times x minus 1 squared minus 24 x minus 1 to the third power. And then because it's a series, it would keep going, right? But it tells us the first 4 terms are just going to be these same 4 terms. And we can see that really is geometric, right? Because remember, if it's geometric, we're multiplying by some common ratio. So we can see on a geometric series, our first term, our A value is just 3. It's pretty obvious, it's the first term. And our R value is what we multiply each time. Well, notice what we're doing each time is to get from one term to the next, we're multiplying that coefficient, the number in front is being multiplied by a -2 each time. But we're also multiplying each term by an x minus 1, right? If I multiply 3 times -2 times the quantity x minus 1, it generates that -6 times x minus 1. If I multiply by -2 x minus 1 again, it becomes a 12 x minus 1 squared. If I do it again, we're back to -24 x minus 1 cubed. So it's kind of a sneaky little way of introducing geometric series, I think. And so we've got this geometric series that looks like this, and it says, find the series, the sum, right? Remember, what we're learning right now in Calc BC, the only series that we actually know the sum of, right? We've talked a lot about convergence and divergence. We've talked about the alternating series, right? P series, the ratio test. All of those things will tell us whether the series converges or diverges. What it doesn't tell us is what it converges to, right? Converges means there is a sum, there is a limiting number of those partial sums as n approaches infinity. If we kept adding numbers forever, the sum, the total would approach some specific real number. Well, we don't know how to find that unless the series is geometric. That's the only one right now for calculus. Now, there are ways, by the way, to find other sums, right? It's not like you can't ever find them, but there's a lot of kind of simple looking series that we know converge. We still don't know what the sum is. It's still difficult to find the exact value. But for geometric, we have a nice, tidy formula that says the sum of a geometric series is just going to be a over 1 minus r, as long as the series converges. And that's if, right, the series converges, meaning if the absolute value of r is less than 1, right? A geometric series converges if that common ratio is strictly between -1 and 1. The absolute value of r is less than 1. Well, we actually know our r value, and they're even telling us an x value. And so at x equals 5/4, right, that's our given x value, then we know that our r value is going to be -2 times 5/4 minus 1. 5/4 minus 1 is just 1/4, and -2 times 1/4 is just -1/2. And so at 5/4, our r value is just -1/2. And the absolute value of -1/2 is obviously 1/2, and that is less than 1. So we know that this series converges using the geometric series test. So not only do we know it converges, it says find the sum. And so we can use our formula. The sum is going to be a, the first term, which we already realized was 3, over 1 minus r. Well, r in this case was -1/2. So it becomes 3 over 1 minus -1/2, which just becomes 3/2. And then using some properties of fractions, we multiply by the reciprocal, and we get 2. And so in this case, this geometric series does converge. And not only does it converge, we know that it converges to the value of 2. There you go. So moving on to the very last part, this is kind of a tricky question. It says, okay, here's a new function, right? We're going to introduce a third function now called h of x over 2. It says here's a piece, a portion of h of x over 2. So we don't know what happens over here, over here. Explain why this function could not be the graph of f. So explain why this could not be the graph of f. So how in the world will we be able to explain that it's not the graph of f? Well, for f, the only thing that I know is certain values when x is 1 and when x is 4. So we're really trying to figure out, basically, could these two things be the same, right? Well, let's go ahead and find out when x is 1, what happens? Well, if x is 1, it becomes h of 1/2, right? Should equal f of 1. Well, the problem with that is we don't even know what h of 1/2 is, because here's when x is 1/2 is over here. So it should match up with f of 1, but I don't know what this graph of is h of x over 2 is doing over here. So there's no way to know whether it does or does not. It could be, who knows, right? They could match up. And it turns out all of these things, h prime should match f prime and second derivative and third derivative. Well, there's no way to do that at x equals 1. There's no way to confirm that or reject it, because all of those values inside for h become 1/2 values. And so since we don't know what h is doing at 1/2, we don't know if it is the graph of f or not. So we can't say it cannot be the graph because we don't know. It could be, we don't know. But maybe we examine this other value that we know at 4. And so if those two functions, right, if h of x over 2 is in fact going to be the same as f of x, then they should match up at x equals 4. And so h prime of 2, or sorry, not h prime, I should just be h, right? H of 2 should be the same as f of 4, shouldn't they? Because if I plug in 4 to both of those, they should match up. Well, we know what f of 4 is. It's -9/2. So these two things should both be -9/4. Sorry, not -9/2. Well, let's find h of 2. Here's when x is 2, and h of 2 is somewhere down here, and you'll notice there's no scale on the y-axis, right? I was pretty devious. I didn't even give you the y-axis scale. So it is conceivable, isn't it, that these two things match up? Because I don't know how far low it is, but certainly it's a negative value. It's below the x-axis, right? And so these two things could be the same. So there's no way to say it could not be, because it could be, right? Now, I haven't guaranteed they are the same, but I haven't guaranteed they're not the same, because they are both negative values. So if they're the same, then all of these values should pair up, shouldn't they? So not only will f have to be the same as h of x over 2, but their derivatives should match up too. So if we differentiate both sides of this equation, notice on this left-hand side, if I take the derivative, we're going to have to do the chain rule. So it's h prime of x over 2 times 1/2, because that's x over 2's derivative, should be the same as f prime of x. And just like before, when x is 4, these two things should match up. And so 1/2 h prime of 2 should be the same as f prime of 4. If I plugged in 4 for both x values, well, I know that f prime of 4 is a positive 3/2. And so I need this to be a positive 3/2. So this is a graph of h. When x is 2, the slope of this, right, times 1/2 should be equal to positive 3/2. Well, again, we don't have a scale, so we can't guarantee what the exact slope is, but clearly the slope of that's positive, isn't it? So again, there's no way to eliminate these two graphs as not being the same because their points, right, when x is 4, could have matched up because they're both negative. Their derivatives when x is 4 could also be the same because they're both going to be a positive value. So it says explain why it could not be the graph. And so we know that's not the graph. So maybe we dig a little bit deeper. Let's take a second derivative now. If I differentiate again, we're going to get h double prime of x over 2. And then by using chain rule again, multiply by 1/2, which gives me a total of a 1/4 in front, equals f double prime of x. And again, plugging in 4 for x, that means that 1/4 h double prime of 2 should be the same as f double prime of 4. So f double prime of 4 is supposed to be negative 9/4, which is a negative value. Now let's think about the second derivative of h right here. The second derivative of a function, remember, talks about the concavity of the function. And so when x is 2 on this graph, then that means that the concavity right there, second derivative, should be, according to this, a negative number. But if you look at the shape of this graph, it's clearly concave up, isn't it? And so because it's clearly concave up, that means that this value right here has to be positive. 1/4 times some positive value is going to be a positive number. So there's no way it could equal negative 9/4. So we had to get all the way to the second derivative, and we had to know to use that second row when x is 4, because when x was 1, there was no way to compare because we only had a portion of this graph. We couldn't actually see the part that mattered. And so after all of that, explain why it couldn't be. And the reason would be because f double prime of 4 is less than 0, but yet h double prime of 2, which is what would happen when x is 4, is greater than 0, since h of x is, or h of x over 2, right? That's the function we're talking about. H of x over 2 is concave up, where x equals 4, right? So since h of x over 2 is concave up when x is 4, that means that h double prime of 2 is positive, but yet f double prime of 4, according to the table, is negative. Therefore, it could not be the graph of f. That's a really tricky problem. When you see those really hard problems like that on a typical FRQ on a normal year, those things only end up like being like 1 point on the exam. It's so tricky. Students I think, oh my gosh, this is such a hard problem. This must be so important. But they're really the hardest questions a lot of times are worth only 1 or 2 points. And then remember, if it's super duper hard, very few students are earning all the points anyway. And so if we can sneak out 1 point, showing our work, showing connections, a lot of times the exam, if this was a 2-point problem, they might give you a point for trying to compare some of those values. If you compared even 1 or 2 of them along the way, that might be that first point. And then coming to the correct conclusion could be the second point. So showing your work, organizing it is always important, because sometimes you get points just for that. And if you don't show that work organized, we can't award any points if we don't see anything that's matching what we're trying to find. So that's that third question. Definitely got more tricky as we went, right? So be careful with all those individual parts, and don't forget in the Dropbox on this handout, there's one more FRQ as well that you can practice for homework, and the solutions will be typed up and available to you guys later. So thank you for joining, and we'll look forward to working with you on our next AP live session. And that will be covering all the BC integration techniques for the BC exam. So we'll see you then.